Hey guys, Mr. B here, and this is the video for Chapter 12, Section 3 on Newton's third law of motion and the law of conservation of momentum. So, this one, there's going to be some heavy stuff in here, okay? So, we're going to get started, and hopefully this makes sense. All right, so first up is Newton's third law of motion. What is Newton's third law? Now, this is one that a lot of people know because it has a nice little saying for it. And this one basically says, for every action, there's an equal and opposite reaction, right? That's the layman's term. So let's understand, though, what Newton's third law actually says. Okay, so Newton's third law says, whenever one object exerts a force on a second object, the second object is going to exert an equal amount of force back on the first one, but in the opposite direction. Okay, so these forces are called action and reaction forces, and this occurs everywhere. Okay, so any force that you could possibly think of always will have an action and reaction force. Okay, so all forces come in pairs. There will never be a force that's just by itself. So let's take a look at some examples of what we mean here. Okay. So imagine that you're pushing your hand against the wall, or you can take your hand and push it against the table, or wherever you're at. As you do that, you're exerting a force on the wall, or on the table, or on that object, right? This is what we call the action force. That object, though, is also going to be giving a force back on you, and it's going to be equal in size, but in the opposite direction. That's what we call a reaction force. Okay, now we know that these two things are equal because if you take your hand and you push it against the table, it might feel a little bit uncomfortable at first. However, if you push really hard, right? Let's say you push really, really, really hard. Your hand's going to start to become uncomfortable, right? It's going to start to become painful on your palm as the harder you push, the harder the table pushes back against you. Okay? If the table wasn't exerting a force back on your hand when you push on it, you wouldn't feel the table. Like, you would literally just feel nothing. Okay, there's resistance there, right? When you push on the table, you can feel something resisting your hand. That's the reaction force. Okay, that's the table pushing back on you. So all forces, again, come in pairs like this. Here's another example. Think of a swimmer. So swimmers, of course, in order to move through the water, you need to push against the water with your hand or kick with your feet. That's the action force. Okay, so the action is that the swimmer pushes on the water with his hand or his feet. The reaction then is that the water pushes on the swimmer with equal amount of force, but just in the opposite direction, which then, of course, propels him forward. So if we were to look at this diagram here, so the swimmer pushing against the water in the backward direction is the action force, and the water then exerting a force on the swimmer is the reaction force, and that's, of course, what propels him forward through the water. Now, unlike swimming, not all action-reaction forces cause motion. Okay, so here's another example, and this is similar to the one we said earlier, where if you take your hand or your finger and you push it against the wall is not going to go anywhere, right? Now, it's not to say that there can't be motion, but you would need to apply more force in order to get the wall to move, because walls are pretty sturdy, right? But we do know, of course, that if you apply enough force to the wall, you can get it to move. It will fall over. Obviously, you need to be very big and very large and very strong to do this, and we usually use machines to do this, but either way, okay? So pushing against the wall with your hand is an example of an action-reaction force that does not result in motion. Now, you might be wondering yourself, okay, if we have action and reaction forces, they're opposite in direction, and they're equal in size, how come they don't cancel out with each other, right? I mean, we've learned at this point about forces and balanced forces, where you have two forces in opposite directions, and if they're in opposite directions, forces, of course, being vectors, they'll subtract from each other, and you get a net force of 0. How come action-reaction forces don't do that, right? If you have two forces, opposite direction, equal in size, they should cancel each other out. The key thing to note here is that they're not going to cancel each other out because they're acting on two different objects. So in the previous example, you'll notice that the action force is the swimmer pushing on the water. The reaction force is the water pushing on the swimmer. So there are two forces here, but each one is acting on a different object, which means they're not going to cancel out with each other. Now, if both forces were acting on the swimmer or on the water, then yes, you would have these forces cancel each other out, and you get a net force of 0, in which case no motion would occur. But you have to remember they're on different objects. All right, so other than understanding action-reaction forces, the last thing we got to talk about here is momentum. Okay, so what is momentum? Now, most of you probably have a pretty good idea of what momentum is, and you know that things with large momentum are difficult to stop. But let's look at the physics definition, okay? So before we actually jump into that, let's think about an example here. So imagine you have a loaded shopping cart, and you have a small glass marble, and both are slowly rolling towards you at the same speed. If I were to ask you which one of these two objects is easier to stop, a loaded shopping cart, and when I say loaded, I mean like, imagine when you go grocery shopping with your mom and she just packs everything in that cart, right? And that cart is getting pushed at you, not super fast, but at a decent pace. And there's a marble on the ground rolling towards you at the same speed. Which one of those two is going to be more difficult to stop? Probably the shopping cart, right? And that's because it has a larger mass. Now, if we were to take the marble, which maybe would be easy to stop in that situation, but if we took the marble and let's say that we put it inside of some kind of cannon or air gun and we were to shoot it out of that gun at a really fast speed, and then I ask you, which would you like to stop? This shopping cart rolling at you or this marble going like, 500 feet per second? You're probably going to go, I'll try to stop the shopping cart, right? You're not going to stick your hand out and be like, no, I can stop the marble. I'll give it a try. Probably not, right? Now, at that point, the reason the marble is more difficult to stop is not because it has more mass, because it has higher velocity. So when it comes to momentum, there are two things that we need to know of, and that is mass and velocity. Okay? Momentum is essentially a product of an object's mass and velocity, and if we were to define it, it would be how difficult it is to stop the object when it's in motion. Objects with large velocities but little masses have large momentum, or objects with large masses and little velocities have large momentum. Okay? So on the left here we have a bullet. Small object, little mass. But it's traveling at a very, very high velocity. So high velocity, low mass, that gives you a large momentum. On the right-hand side in this picture we have a giant boat, right? And if this boat were coming into port, you probably wouldn't be sitting on the dock going like, don't worry, I'll catch you. I'll make sure you don't hit the dock. Probably not, right? Because this object, although it's probably not moving that fast, has a very large mass. And because the mass is so large, even though we have a small velocity, we have a large momentum. So, momentum is going to be dependent on mass and velocity, okay? If we are going to calculate it, basically momentum is equal to mass times velocity. And we'll oftentimes abbreviate momentum with a P, not an M. And the reason we don't use M is because M stands for mass. So we have to use a different letter, okay? But momentum is mass times velocity. And it has the units of, and I don't know why this is not in here, but it has units of kilograms times meters per second. So the units of momentum are kilograms, which is the unit of mass, times meters per second, which is the unit of velocity. Okay? Those are your units for momentum. So the key thing to note here is that objects that are not moving don't have any momentum. Okay? So if an object is at rest, its momentum is 0. Okay? There has to be motion in order for there to be momentum. Okay, the last portion here is on the conservation of momentum. All right? So what happens to momentum when objects collide? So we're going to look at some collisions here, and we're going to get an understanding of how momentum works. So in our first example, we have two train cars, and one is, let's say they're both the same mass. One is moving 10 meters per second, the other is 5 meters per second. So one's going faster than the other. So the faster cart has a higher momentum of 300,000 kilograms per meter per second. And the smaller cart has, or the slower cart has only 150,000. Now this cart in the back is going to eventually catch up to this cart in front. It's going to hit it, and the cart now that was in front is going to speed away at a faster speed. So it kind of gets like a speed boost. And the cart that was in the back is now going to be going at a slower speed. Okay? And we'll notice that the momentum of the cart before the collision happened, this first cart was 300,000. The second cart was 150,000. But after the collision, the second cart has now gained momentum, and it has a momentum of 300,000. And the first cart has lost momentum, So its momentum is only 150,000. But before the collision occurred, the total momentum of both of these objects combined was 450,000. And after the collision, the total momentum of both these objects combined is 450,000. So the total amount of momentum before and after the collision is still the same. It just got transferred from one object to another. All right, let's take a look at example B here. So in this example, we have a cart, again, moving at 10 meters per second. It has a momentum of 300,000 kilograms per meter per second. And you have a second cart that's not moving. So it has zero momentum, right? It's not going anywhere. This first cart hits the second cart. The second cart, of course, gets knocked away and speeds away at 10 meters per second. And the first cart now comes to a dead stop. So we can see that all of the momentum that the first cart had gets transferred to the second cart. And now the second cart has all the momentum and the first cart has none. But the total amount of momentum before the collision was 300,000, and after the collision, it's still 300,000. All right, lastly, let's take a look at example C. So in this one, again, we have a cart that is moving at 10 meters per second, a cart that is not moving. But let's say that the first cart hits the second cart, and rather than the second cart getting knocked away and the first cart stopping, they hit each other and then they move together, okay? So at this point now, the first cart was going 10 meters per second, it collides with the second cart, and they move together, and all that momentum that the first cart has is still there, but now, rather than moving at 10 meters per second, they're moving together at 5 meters per second, okay? So we've lost half of the momentum that we had before. So again, we can see that we have a amount of momentum here, but it gets shifted, and in which case, the total amount of momentum before and afterwards is still the same. Okay, is what we call conservation of momentum. So in each collision, there's momentum before and after, and as long as the system you're dealing with is closed, which means no other forces can act on these carts, there's no friction, there's no air resistance or whatever, then the total momentum of the system does not change. So all the momentum that the first cart has gets transferred to the second cart. You know, granted, in real life, there's always going to be other forces acting because we can't create a closed system in real life. That would be too difficult. But the concept still applies, okay? So basically, again, if one object loses momentum, that momentum has to go somewhere. It doesn't just disappear. So, all right, that is it for this section of notes. Hopefully that makes sense. It's a little bit of a tricky section. There will be some practice going forward with some quizzes practice. So when you get to that point, hopefully then maybe you can clear up some confusion. But if you need any help, reach out to me, and I have no problem sitting down and helping you. So, all right, guys, that's it for this section. That's it for the chapter. I'm Mr. B. Thanks for sticking with me, and I'll see you in the Chapter 12 review. Bye.